Okay, I now want to talk about how one makes use of what we're going to come to know as a probability distribution. So suppose that we have a number of possible mutually exclusive exhaustive inferences. For example, suppose there's a possible variable called x. The variable x might be able to assume different values. But let's say those number of values that x can assume is finite and that x is a discrete variable. That is to say, x can't assume every possible value, but x will be able to assume certain values. So let's say we have a variable x, where possible values possible values of x are x1, x2, x3, x4, x5, and wherever and somewhere it's going to stop. That is to say, there are n possible outcomes or n possibilities for x. And we would like to ask the following question. We would say we don't actually know exactly what value x is. We know that x, when it's measured, for example, maybe it's the energy of something, the face of a die, the number on a die, or whatever it might be. When the value of x is measured, let's say in an experiment or in a trial, any one of these outcomes could be found. That x can range from the first value x1, whatever that number is, to the final value xn. Maybe this is 1, maybe this is 1,000, whatever it might be, whatever numerical outcomes. But we imagine x is a number. And that number can assume different values, and any one of these n possibilities can be found for the variable x when x is measured, let's say, in the lab, or calculated some way after measurement. We associate with each one of these outcomes a probability. That is to say, when x is measured, we cannot for certainly predict what the value of x will be found. We know it can't be anywhere outside of these numbers. It's going to be one of these outcomes. But we don't actually know exactly what value there is. And so our degree of rational belief then assigns some way, it's not clear how, but some way it assigns a probability to observing a particular x. We would say there is some probability of observing the inference that x is equal to x1. There is some probability that the inference is x equals x3. There will be some probability that x is equal to xn. The set of these probabilities for the possible values of x, for the possible inferences, for the possible outcomes, is called a probability distribution. So what this might look like is you might imagine being able to make a plot of p of x, where x is a discrete variable. On the right-hand side, maybe we'll order the values of x, and you will have an outcome x1, an outcome x2, outcome x3. They don't necessarily have to be equally spaced in this line, but whatever. All the way up to xn. And so you could plot, in principle, these probabilities. Perhaps the probability of p of x for when x is equal to x1 is this. Maybe this is for x2. Maybe this is for x3, x4, and so on. Maybe this is 0. Maybe it's never xn. Seems a little weird, but you never know. Of course, any one of the probabilities cannot be larger than 1. Oops, that one is larger than 1. Fix that. Put that over here. We also know that one of the values of x will be obtained. And so the normalization condition, once again, let's remind ourselves, says that if we sum over all the possible probabilities, we expect to get 1. That is to say, x is definitely some value in this range. And then when it's measured, some value will be found, so that when your inference is the probability that x is equal to x1 or x is equal to x2 or x is equal to x3 and so on, where any one of the answers satisfies your net inference, the answer will be certain. It'll definitely be 1 because one of the outcomes will certainly be obtained. And so we remember this as a normalization condition. A common question, so once again, this is called a probability distribution. We will see more complicated probability distributions in this class, but the idea will not change. The idea is that there is some variable that fluctuates, that isn't always equal to the same number, and that it has a different possibilities for the value of that number. And our degree of rational belief somehow allows us to assign a numerical value for the probability that when x is measured, x is in fact equal to x1. Or when x is measured, x is in fact equal to x3. We can't guarantee it, it's not certain, but we have some, in principle, somebody came down and gave us a degree of rational belief in all these numbers were added together. If they're mutually exclusive and exhaustive, add to 1. A common question to ask of a probability distribution, a common question to ask in a problem like this, and this will not be unfamiliar to you, is on average, what is x? Suppose x was measured many, many times, and yes, it fluctuates, but on average, what is x? A probability distribution allows you an algorithm, a recipe, to determine the average value of x, given the probability distribution. The recipe is as follows. Board comes out, board rotates, going back, okay, and let's erase. Okay, we want the average value of x. Average value of variable x. Again, x is a discrete variable. It can assume particular values, but not every possible value. Another name for this is going to be expectation value. Expectation value of x. Another way of saying this is the mean value of x. For our purposes, these questions are synonymous. The average value of x, the convention that we're going to be using is to use angled brackets. This is the average value of x. The recipe, given the probability distribution, is that once you're given a probability distribution and you know the values that x can be, you know the values of the outcomes. The recipe is as such. Sum on all possible outcomes from 1 to n of probability of obtaining a specific value of x times the actual value of x. And so in a sense, the probability weights the significance of a specific outcome. Your degree of rational belief is dialing in its contribution to the average value. If all the outcomes are equally likely, or the probabilities in front of all the possible values of x will be the same. Most of the time, that's not true. And so this is the mean value or the average value of the variable given its probability distribution. The sum, the set of all of these probabilities for each value of x, that set is the probability distribution. And so we're using the probability distribution and the value of x itself of a specific outcome I, whether it's 1 or 2, 36, 59. That product for every possible value of x, of the probability to obtain that x times the value of x, all of them get added together, and that sum holistically represents the average value of x given a probability distribution. The average value of x is called the first moment of a probability distribution. That's kind of one of the formal names for it. There's this idea of a second or third moment of a probability distribution. So you could be asking for the value, the average value of x. But suppose you were interested in kind of a, maybe unexpected question. What is the average value of x squared? Suppose x is still the same variable, it can assume the same values, but the quantity that you're interested in now is no longer just the value of x, but the value of x and then squaring it. The recipe, the algorithm to calculate the average value of x squared looks very similar. The probability, once again, weights that a specific x is actually found when the variable x is measured. That when you measure x, you find a specific x of I, times not the value of x of I, but the value of x of I squared. And so the algorithm looks like, for each value of x, find the probability that that x is obtained, and if that x is obtained, or given the likelihood that that x is obtained, here's the actual value of x squared when x is that specific value, x of I, maybe x36, the 36th value of x, whatever it might be, 1,000,000,000, 5. You can see that x raised to any power, the average value of x raised to any power, is going to be found by an identical or nearly identical summation, where we will write as the first term the probability that x is that specific value times the value of x when it is that specific value raised to the nth power. This is the total number of possible outcomes, the total number of possible values of x. This is just some power that you're interested in for some reason that we have no way of anticipating yet, but it will become relevant. The average value of x raised to a specific power is found by running the index I over all the possible outcomes that x could be, from xi to x1 to x2 to x3 to x sub big N. Probability that that specific x is obtained times the value of that x, x sub I, raised to the power that you're interested in. One can generalize this a little bit further. Say, what's the probability of a specific function of x? Suppose you're interested in a more complicated function. Suppose the function that you're interested in is x squared plus 5x minus 7, some random quadratic equation, or square root of x, or a logarithm of x, or a logarithm of x plus square root of x. Some completely arbitrary function of x. That is to say, when x is found to be a specific value, x of I, the value of the function then is determined. The function could be arbitrary, like logarithm of x plus square root of x. When x is xi, plug in xi into the function spits out an outcome, or a numerical value. So the average value of any arbitrary function of x, you can see that the algorithm is going to look like this. Probability that x is a specific value times the value of the function when x is that specific value. The function being completely arbitrary. It could be either the minus x, a function that we'll see a lot in this class. It could be a logarithm of x, another function we'll see a lot in this class. I think you understand the point there. Let me just mention that, just again, notation-wise, the average value of x squared is also known as the second moment of the probability distribution. This is the nth moment of the probability distribution. We will have occasion to use both the first moment, the average value, and the second moment, the square of the variable average, in this class, and we'll see how that naturally comes about in the statistics and then in the statistical thermodynamics that we do in this class.